and angle measures in triangles. Oh my gosh. Oh, it's probably classified. That would make sense. It's the first blank. Can't even remember what goes on the first blank. Okay, so this we've seen before. It's just a reminder. So acute triangle has how many acute angles? 3. Okay, what about equiangular? Okay, 3 congruent acute angles. Right triangle, 1. Obtuse, 1. Okay. We've already talked about how the bigger the angle, the bigger the side is going to be needed to like cover up the angle, right? So we decided that if we had 3 of the same side angle, we would need the same side opposite each of those. Okay, so if we have an equilateral triangle, it's also equiangular. All right, so we have 3 congruent sides, at least 2. So like you were saying earlier, any equilateral triangle is also isosceles. Do I need to do the Venn diagram again? Or, okay, we were all still traumatized, it's fine. 0. Yep. All right, we're ready to rock. All right, we have to find the side lengths and then classify completely. Any ideas? Yeah. Yeah. Okay, so if I know that the sides, the segments are congruent, what do I know about the measures, the lengths? They're equal. It sounds like an equation to me, right? I don't even have to rewrite it. I can just put an equal sign right there. You know what I mean? Don't work too hard. All right, so I can subtract away 2x from the 4x. I get 2x. 6.3 plus 10.7. I'm getting 17, but I'm notoriously bad at mental math. Dividing by 2, 8.5. All right, so I still have to plug that in. So I'm going to substitute that for all of my x's. So at this point, have I even used the bottom? No, I didn't need it for my equation. It was extra information. The only reason that I have it in my problem is, 1, to see if I know when and when not to use it. And now I'm going to use it just to figure out my side length. Okay? All right, which of these looks friendlier? Well, let's do them both and make sure we get the same thing. So 4 times 8.5 minus 10.7, and we'll also have 2 times 8.5, I'm just substituting in, plus 6.3. And if our answer is correct, we should get the same thing for both of those. So, what is it? Let me make sure I'm doing it on the right thing. All right, and then just plug it in for the bottom. Also substitute. So 5 times 8.5 plus 2 for this one. What is it? Okay, let's just double check and we don't make sure we don't have to put units on anything, like they didn't sneak some inches or centimeters in there. I think we're good. Okay, so what would this classification be? It is isosceles. Okay, so this is in terms of sides. So I can still also classify it by angle measures. Yeah, it's very obtuse. So this is by angles. Okay, easy enough. Okay. Recall, okay, we've already heard about this. So this should be a review because I yammered on about it yesterday. We know that an isosceles triangle has at least two congruent sides. So this one has just been turned on its side. We usually see where it's marked like this way, but it's just rotated to mess with you. The congruent sides are called the legs. The vertex angle is the angle formed by the legs. So that would be this one. I think I might have seen it in other textbooks and sources where it might be called the apex angle, which I kind of prefer to vertex angle because really aren't they all vertices? Like that one just doesn't, that one seems a little bit nonsensical. Like it doesn't tell us as much as apex. Apex sounds like something. Okay, the side opposite the vertex angle is called the base. Okay, so once and for all, does the base have anything to do with which side the triangle appears to be resting on? No. It's opposite the odd man out angle. Okay, we got the two matching angles. It's between the two matching angles. So wherever those are, even if it's up on top, that would be the base. Okay, it has nothing to do with which side it appears to be resting on. Because I could turn this, you know, with the rotation, and this is still the base. Is that okay with everybody? Okay. The base angles are the two angles that have the base as a side. So this is a base angle, and that is a base angle. I didn't label my legs. This is a leg, and this is a leg. Kind of makes sense. All right. All right, I've already mentioned this. It's probably like textbook name is called the Isosceles triangle theorem. It is also commonly known as the base angles theorem. I almost prefer this name just because it tells you more about what it's talking about. Like the Isosceles triangle theorem could mean anything, right? But the base angles theorem tells me that my base angles are congruent in an isosceles triangle. So if I have two sides of a triangle congruent, then my angles opposite those sides are also congruent. So if I have an isosceles triangle, then my base angles are congruent. This is actually one of those special if and only if times where the logical statement is true backwards and forwards. So we also have the converse of the base angles theorem. So if we have congruent base angles, okay, then we have an isosceles triangle, and it has to be the two sides that are opposite the base angles. It can't be any two sides you want. Here, I'll put in my little congruent symbols so that you can see it has to be the ones opposite. So I can't do that. Does everybody see what we're saying? It has to be the ones that are opposite. Okay. All right. Here's the thing. When you are writing your proof, if you're like writing it out by hand, I don't care if you call it the base angles theorem or the isosceles triangle theorem. I don't care, and same thing with this one. You could call it the converse of the base angles theorem or the converse of the isosceles triangle theorem. If I am supplying them in like multiple choice, you're obviously going to have to recognize the real name. Does that make sense? Okay. All right. Okay. Complete our flow proof. Guys, we are going to have to draw our own arrows. This is exciting. I'm just talking about how much we love proofs. Okay, so what have we been given? Yeah. Yes, okay, so here I have two given angle measures on my picture, and those are already here. Do you guys see that? So I wouldn't put these in that bubble because they're already on there. So this one has been given to us from the picture, and this one has also been given on the picture. So as we said, yes. Okay. GH is congruent to JH. Okay. What does that information tell me about my triangle type? It's isosceles. So this bubble sends me to this bubble, and it tells me that triangle, doesn't matter the order of the letters? No. GHJ is isosceles. Okay, so if I know that I have an isosceles triangle, what do I know about these two angles? Correct. Because of what theorem? The base angles. So now that I have said my triangle is isosceles, I can use that information to say that my base angles are congruent using the base angles theorem. Okay, so far so good? Okay, what do I know about the measures of congruent angles? Yeah, the measures have to be equal. And that comes from the definition of congruent. If I know that angle J is congruent to angle G, then I can say the measure of angle J is equal to the measure of angle G. So that came from there. This is a flow proof. Have you guys seen one of these before? It's kind of fun. It kind of shows you, like, when you write a two-column proof, everything you need for your proof has to be like up above somewhere. But this shows you directly how the logical argument flows, and it's kind of cool to see. Okay, so now that I have an equation, do I know what the measure of angle J and angle G are? Yeah. So what's to stop me from placing them into that equation? What property allows me to swap like that? Yes. It's our good old-fashioned friend, the substitution property. Okay, so this bubble is weird because I needed to have the equation to make this bubble, right? I also had to have the stuff to substitute into the equation to make that bubble. How do you like that? You should have seen me on the computer trying to figure out where to put all these bubbles. My head almost exploded. Facts. All right, now what? Yeah. So what are we subtracting away? X from both sides. I'm going to stay with the blue, actually. So now I have 2x equals, correct. Okay? Division property of equality. So this step came from there, and this one takes us home. Division prop of equality. So just kind of twisted and turned all over the place. Yes, ma'am. Okay. All right. Was that the end of this page? No? Oh, yeah, we do have to answer. Oh, thank you. Thank you, quality control. Okay, so now we need the measure of angle G. Now, wouldn't it, we know that these two are supposed to have equal measures, right? What is an excellent way, like the easiest way ever to make sure that our answer is correct? Do both, right? It'll take you 2 seconds to put 3 times 22 in the calculator. You can probably do it in your head. What's 3 times 22? Yeah. So we should make sure that 22 plus 44 is also 66. Is it? All right. We are amazing. Don't forget the degrees. Hey, did everybody get that? Test it in both because you will catch more mistakes that way. How do I know? Because that's how I catch most of my mistakes. Because that's the mistakes I make. All right. I heard someone say they'd rather just do a 2-column proof. No one said that? No, that's so weird. All right, so over here, these are our statements. What goes on the other side? Close? You can say justifications or reasons. Doesn't matter, it's the same thing. Oh my gosh. What if I could spell? Justifications. Okay. How do we know that DE is congruent to FE and that the measure of angle E is 22 degrees? Given. Okay. What can we get from the definition of an isosceles triangle? What about angles? Okay, we know that. Doesn't that help us classify this triangle? Yeah. Yeah, we just can say that that's its classification. Triangle DEF. Okay. All right, now what? Base angles theorem, what does it say? Someone said what? She was just looking ahead. So the what is, if I know that triangle DEF is isosceles, what can I say about this angle and this angle? Okay, we're going to forget I did that. We're just going to draw it like this instead. I don't know, I mean, that's slightly better. Who picked this stupid looking triangle? All right. Golly. You think you can go through one day without drawing something phallic on the board, but it's impossible. All right, it's fine, it's fine. We're grown-ups almost in here. Okay, so if this is isosceles, then I know that my base angles are congruent, and that comes from my base angles theorem. Okay, so I know that angle D is congruent to angle F. And I'm allowed to name them by one letter because they are the only angles that have that vertex. Okay, the minute I add another angle that shares that vertex, I have to use other letters. Do you guys remember that from Unit 1? Okay. So how do I know that the sum of the measures of angles E, D, and F is 180 degrees? We learned this yesterday. Starts with triangle. That is correct. I really feel like it should say, like, triangle interior measures sum theorem, but that didn't really catch on, so it's kind of a mouthful. What do you think I'm going to put here? Yeah, I'm going to make substitutions. Now, I'm going to be... Oh, shoot. I think I might have skipped a step in the proof. Okay. All right, it's not a big deal. Okay, so what do I know is the measure of angle E? Yeah. Okay. Now, I haven't written this yet, but what do I know about the measures of angle D and angle F? Okay, the angles are congruent, so the measures have to be equal, okay? So it doesn't matter if you put it here or here, but before you do the substitution, you need a missing step that I forgot to do because I was doing this in my head and it was probably late. So you need to tell me that the measure of angle D equals the measure of angle F. Okay, and that comes from the definition of congruent. I'm sorry that I missed it in my head. Does everybody see why we need that step before we make our substitutions? Here's the thing, if we only have one unknown, we can solve the equation for the unknown. If I have two unknowns, can I solve that equation? Thank you. All right, so now that I've said that these two are equal, I want to find the measure of angle D. So do I want to keep angle F around anymore? Is that the one I'm solving for? No. It really makes no difference because we know that they're congruent. But if I use angle F instead of angle D, it just adds more lines to my proof. You see what I mean? Like you can keep it shorter by just using D instead of F. Okay, so I know that D is equal, measure of D is equal, so I'm just going to put in measure of angle D plus the measure of angle D has to be 180 degrees. Yep, that's the substitution property. It's going to be a fun video to watch with your family tonight. All right, now what? Do you guys want to combine like terms or subtract away the 22? It doesn't matter which one we do. Okay, let's combine. So I'll have 22 degrees plus how many measures of angle D? 2. You subtracted, but you didn't tell me you were going to subtract. So someone else said combine like terms. So now we'd sound like we don't know what's going on. All right, so we just did the substitution property again. All right. Okay, now tell me yours. Did you say 158? We could have done this one first and then combined the like terms. So this one is substitution property again. Nope, I lied, it's not. What is it? Subtraction property of equality. Okay, last but not least, division property of equality. Ooh. So the measure of angle D is, did you say 79? Yeah. Division, thank you. Okay, that wasn't the worst. Okay, we laughed, we cried, we did math. All right, so remember that corollaries are fun little logical extensions from theorems that we already know. So a corollary is a theorem whose proof follows directly from another theorem. So they're kind of like little freebies. Okay, if a triangle is equilateral, then it is also equiangular. All right, we already knew that. So this one is just the reverse. If we know that it is equiangular, then we also know it's equilateral. If you know one, you know the other. It's not true for all polygons. You get enough sides, and then you can have a figure that's called convex or concave. We can talk about it right now. So with just 3 sides, I can't really have like a dent in my polygon, but once you get up to 4 sides, I can have a polygon that looks like this. You see it 1, 2, 3, 4. Okay? You see how it kind of has a cave in it, where it caved in? That's concave. Okay? So there are certain polygons where you can have the same length of side, but the interior angles are different measures. I think the one I'm thinking of, picturing in my mind, if you can bear with me, is an octagon. Oh, geez. Oh, geez. Okay, imagine that I'm drawing this correctly to where all the sides are congruent. So right now I already have 1, 2, 3, 4, 5 sides, and I could have all of these sides congruent, but are my interior angles congruent? No. So this is special for triangles, that if it's equiangular, we also know it's equilateral. For other polygons, we have to like say that they're regular, which means that they are equiangular, equilateral, and convex, that they don't have any dents, because dents ruin everything. That makes sense to everybody? Kind of? Okay. All right, here we go. We have to find the side lengths for this triangle. Well, I see that I have an equiangular triangle. What does that mean for my sides? They are all congruent, therefore they all have the same length. Now, some kids will get confused by trying to set all 3 of these equal to each other. Do I need all 3? No, I just picked my friendliest looking 2, as long as they all have the same variable. Like if one of these had x in it, I wouldn't use that one. I'd use the one where I could solve for the variable. And then I use the third side to make sure that they all come out the same. Right? Okay. So which 2 look friendliest? All right, I just heard mumbling. I'm using these 2. So I'm using 3y minus 4 equals 2y plus 3. If you wanted to use the bottom one, that's fine. Just make sure you get the same thing that we get. Subtract away 2y, we get y. Add over the 4, I get 7. Now we should test the 7 on all the sides and make sure we get the same thing. All right, so 3 times 7 is 21 minus 4 is 17. Okay, 2 times 7 is 14 plus 3 is, so far so good. All right, this one. Bam. All right, GH, 17. Okay, make sure there aren't any units hiding anywhere. All right, what classifications can we put on here? Equiangular, I heard another one. Yep. Okay, so we also know that it's isosceles, which is less specific, but if it was like a select all situation, we could also select isosceles because that's true, isosceles. Okay, for triangles, if they are equiangular and equilateral, we call them irregular. Okay, I can think of one more classification by angles. Is 60 degrees, 60 degrees, 60 degrees all less than 90? That's you. That's the last one I can think of. Okay. Woo! All right, do you guys want to try another flow proof, or do you want to try the one at the bottom? I don't know that it, do you want to work from the angles, or do you want to work from the sides? Doesn't matter. This is the converse, and then this would use the normal corollary. Okay, let's do this one. Let's use the converse. We'll do it tomorrow. We'll do it tomorrow. I don't think there's enough time.